In the previous sections, we were dealing with the law of sines, which says that A over sine A is equal to B over sine B is equal to C over sine C. And in order for the law of sines to work, or in order for us to be able to use the law of sines, we needed to know at least one side and the angle opposite that side. If we didn't know a side and its opposite angle already, we wouldn't have enough information to plug into these equations and solve. We'd be left with two unknowns and we couldn't solve them. I'll show you an example of that here in just a second. So for the law of sines, we needed to know at least one angle and the side opposite of that angle. It doesn't have to be A. It could have been angle B inside B or angle C inside C. I'm just using A here as an example. So we needed to know an angle and the side opposite that angle, and we needed one more piece of information, either another side or another angle, right? Either another side or another angle. And so there was two different situations that we were dealing with there. One of them was when we knew two sides and an angle. We call that SSA. Right, so two sides and an angle. Or, instead of knowing two sides and an angle, we could have known two angles and a side. And so we'll call that side, angle, angle. Now, when we know a side and two angles, we can go directly to using the law of sines. There's only one possible solution that makes this triangle be true, right? So side, angle, angle, there was always only one possible solution. But if we knew two sides and an angle, again, for example, maybe we know side A, side C, and angle A. If we know two sides and an angle, that was when we had the situation of the possibility of there being no solution, only one solution, or possibly two solutions. And so we had to determine the number of solutions. We didn't know off the bat how many solutions there would be. Now consider a triangle with angles A, B, and C, and sides A, B, and C. And let's say, for example, that we know two sides and an angle, very similar to this, but instead of being two sides and an angle that is not the included angle, let's say that we knew two sides and the included angle, the angle that was in between. That will not lend itself to the law of sines, because I don't know an angle and the opposite side. I don't know an angle and its opposite side. I don't know the angle and its opposite side. I have three pieces of information. I should still be able to solve for this triangle. There's only one possible solution, but I can't use the law of sines. Any form of the law of sines that I try to use with this information, with two sides and an included angle, is going to leave me with two unknowns in the formula. And so we call that SAS, where we know a side, an angle, and a side, and that angle is the angle in between the two known sides. Right here, the angle is not the angle in between the two known sides. Right, B is the angle in between the two known sides. This angle is outside. This we could use the law of sines because we know the side and the opposite angle. Here, though, we have a different situation. We can't use the law of sines to solve this triangle. Though we should still be able to solve it, we just can't use the law of sines. The other possibility is where we have a triangle where we know the length of all three sides, but we don't know any of the angles. And so we call that SSS. Side, side, side. Again, here we don't know any angle, therefore we don't know an angle and its opposite side. There's no form of the law of sines that we can plug this information into and get an answer. We're going to end up with equations that have two unknowns. And so if we know side, angle, side, or we know all three sides, we cannot use the law of sines. Rather, we need to know the law of cosines. Before we can apply the law of cosines and use the law of cosines to solve triangles, we need to first derive what the law of cosines is and see where it comes from. So what I have here is an xy coordinate plane with an x-axis and a y-axis. I have a triangle in the plane where one of the legs of the triangle is directly on the x-axis, and then I have a height that comes up perpendicular off of the x-axis to point C. And so the triangle is in our standard position. We have angles A, B, and C, and we have the sides opposite, which are A, B, and C. And so to derive the law of cosines, I first want to look at this triangle, right? So the height or the altitude formed two right triangles out of this one triangle that was not originally a right triangle. So now I have two right triangles. I want to look at this triangle. I'm going to call this point right here, let's call this point D. D is the point of the where the right angle is for each of these two triangles. And so I know that the hypotenuse of this triangle is B. Whatever the length of B is, that's the length of the hypotenuse. I know that the length of this leg of the right triangle is the height, or H, but I don't quite know what the length of this side is yet. I'm going to call that G. Okay, I don't know what this length is yet, but I'm going to call it G. Okay, and likewise, I want to look at this triangle. The hypotenuse of this triangle is A. The one leg of the triangle here is also the altitude, which is H. And then this length of the triangle, I don't really quite know what that is yet. I know that the entire base of the big triangle is C. This distance is G. And so that means that this distance here in between must be C minus G, right? Whatever C is, if I take away G, I'm left with C minus G. And so this distance will be C minus G. Okay? And so what I want to do now is I want to apply the Pythagorean theorem to this triangle. And so first thing I want to do is call out what the xy coordinate of this point is, also what this point is, the xy coordinate, and also the xy coordinate of this point. So this point, the x coordinate is what I'm calling G, right? That's how far away it is from the y-axis. The x coordinate is G. The y coordinate is H. For this point, actually let's look at D here. The xy coordinate of D is going to be G. The x coordinate is G. That's how far away it is from the y-axis. And the y coordinate is 0. And then let's look at this point. The xy coordinate of this point, the x coordinate is C. And the y coordinate is also 0. Okay, so let's use this information to apply the Pythagorean theorem to the triangle, the right triangle here on the right. So the hypotenuse is A. Pythagorean theorem says that the hypotenuse squared should be equal to the sum of the squares of the other two sides. And so this side of the triangle, its length is C minus G. So this side, the length of this side is C minus G. Pythagorean theorem says to square that length and then add to it the length of this side. And the length of this side is H. Okay. And so I have the Pythagorean theorem written out for this triangle, right? The hypotenuse squared, which is A, is equal to the square of the other two sides added together. The length of this side is C minus G, so that's being squared. Length of this side is H, so that's being squared. And so now what I want to do is work this out some, and I want to actually FOIL this out. Let's FOIL this out. And so what we're going to get is A squared equals, when I'm squaring a binomial, that means I'm taking C minus G and I'm multiplying it by itself. So I'm going to apply the FOIL method here, plus H squared. And so when we use the FOIL method, we do first, outside, inside, and last. We'll multiply all of those terms together. And so we get C times C, which is C squared. C times a negative G, which is negative CG. We get negative G times C, which is also negative CG. And then negative G times negative G, which is going to be a positive G squared. And then also I have this plus H squared out here. And so I do have some like terms here. I should combine them. So A squared equals C squared. I have two negative CGs, so that's going to be minus 2CG. Right? That's combining those like terms. Plus G squared plus H squared. Okay, so this is the Pythagorean theorem applied to this triangle. Right? So A squared is going to be equal to C squared minus 2CG plus G squared plus H squared. Now I want to apply the Pythagorean theorem to this triangle, and I'll write that over here so it's kind of out of the way. In this triangle, B is the hypotenuse, right? So B squared equals, the length of this side is G, right? The length of this side is G, so that'll be G squared, plus the length of this side squared, which is H squared. Okay, and so notice that G squared plus H squared is equal to B squared. And in this version of the Pythagorean theorem for this triangle, I have g squared plus h squared. And since g and h are the same values in both equations, right, their lengths are equal for both equations, I can make a substitution here for g squared and h squared. I know that that's equal to b squared. So I'm going to make that substitution. A squared is equal to c squared minus 2cg plus, and instead of g squared plus h squared, that is b squared. So I'm going to write b squared here. Okay. And now I'm just going to kind of rearrange the terms a little bit. I'm using the commutative property. I'm allowed to rearrange the order that the terms are written in. So I'm just going to kind of clean this up a little bit. I'm going to put the b squared over here. Right, that's positive. I'm going to put the c squared after it. It's positive. And then I'm going to write the minus 2cg after that. Notice that this looks like the Pythagorean theorem, right? If I got rid of this minus 2cg, this would just be the Pythagorean theorem. Okay, so I still have this term out here, and this helps me. This is going to help me derive the law of cosines. The last thing I want to do is look at angle A. The cosine of angle A is going to be the adjacent side, which is g, divided by the hypotenuse, which is b. Cosine of A is g over b. And what I want to do here is multiply both sides by b, so that b cancels. And we get g equals b times the cosine of A. The reason I'm doing this is because I know the values of, or I potentially know the values of the three sides A, B, and C. I potentially know the three angles, angle A, angle B, and angle C. G is really an unknown value. I'm not really sure what that is. H is sort of an unknown value. I don't really know what that value is either. And so my formula here has A, B, and C in it. Those are the lengths of the three sides. I also have a C here, which is the length of side C. But I have this G here, and that G is a value that's not really part of the triangle. You know, that's not one of the three sides of the big triangle. So I'm trying to get rid of G. And that's why I've taken the cosine of A to be g over b and solve for g, so that I can make a substitution here. So g is b times cosine A. So instead of g, I'm going to write b times cosine A. So we get a squared equals b squared plus c squared minus 2 times c times, and instead of g, I'm going to write b times the cosine of A. Okay, and then I'm just going to clean this up a little bit. I'm going to use the commutative property again to change the order of b and c here. I want them to be in alphabetical order. Okay, and so now I have a formula that deals with a triangle that is not necessarily a right triangle, that all of the variables in the formula are lengths of sides like A, B, and C, or B and C, or angles of the triangle like A. Okay, and this is the law of cosines. We've derived the law of cosines. And so I focused on a height that went from side C up to angle C. I could have drawn an altitude from side B to angle B, or from side A to angle A. I could have had three different options here of where to draw the altitude. And depending on where I draw the altitude was going to affect this formula slightly. And so I could, if I drew a different altitude, and I had two other options, I could have gotten b squared is equal to a squared plus c squared minus 2ac times the cosine of b. This is another version of the law of cosines that I could have derived if I had drawn the height in a different location. I also could have gotten c squared equals a squared plus b squared minus 2ac times the cosine of c. And these are the three versions of the law of cosine that we're interested in. So the law of cosines is going to help us to solve triangles that deal with known information of, for example, I know a side, an angle, and a side. So just like we talked about a few minutes ago, if I have a triangle where I know two of the sides and I know the angle included, I can't use the law of sines to solve that triangle. I'm going to have to use the law of cosines. Also, we could have triangles where we know all three sides. Again, I can't use the law of sines for this. I'm going to have to use the law of cosines. You're going to want to familiarize yourself with these three forms of the law of cosines. And so, notice that they sort of resemble the Pythagorean theorem. A squared equals b squared plus c squared. But then we have this extra term over here, minus 2bc cosine A. And so notice whatever the side is over here by itself on the left hand side of the equal sign being squared, that's the angle opposite of that side that I'm taking the cosine of. So if I see a squared equals, I expect cosine a. If I see b squared equals, I expect cosine b. And if I see c squared equals, I expect cosine b. And then as far as the minus 2 BC part, the b and c are the two sides that are on the right hand side. So here if I have b squared plus c squared, I expect 2bc because it's b and c. And if I see a squared plus c squared, I expect 2ac, right, because it's a and c. And if I see a squared plus b squared, I expect 2ac because it's, I'm sorry, look, I made a mistake. It's going to be a and b, right? If I see a squared plus b squared, I expect 2ab. So familiarize yourself with the three forms of the law of cosines. They're really all the same because I don't have to label this angle A, angle B, and angle C. I could have called it angle A, angle B, and angle C, right? I could have called it anything that I wanted. And so the law of cosines applies to any triangle. But if you're drawing your triangles in a standard layout like this, where we label the lower left angle as A and then move counterclockwise to label them B and C, and then have the opposite sides be A, B, and C, the opposite sides of those angles. If you're drawing your triangles in those standard positions, it will be helpful to familiarize yourself with the three forms of the law of cosines. That'll make it less confusing, I hope. It'll be more clear as to which sides you know and which sides you don't know. So if you're labeling your sides as A, B, and C, you'll know that perhaps you know sides A and C, but you're looking for side B, and maybe you know angle B. Okay, and so familiarize yourself with this. That'll be helpful to you in the long run. This is example 1. It says if A is 112 meters, B is 135 meters, and C is 104.3 degrees, solve the triangle. And so we'll want to sketch out the triangle first. That'll help us visualize the problem. And so our standard triangle, we have angle A, B, and C. And we have sides A, B, and C. And so side A is 112 meters. Side B is 135 meters. And angle C is 104.3 degrees. And so notice that I don't have enough information to use the law of sines. I don't know an angle and the side opposite, right? I don't know an angle and the side opposite, or this angle and that side opposite. So I cannot use the law of sines to solve this triangle. I'm going to have to use the law of cosines. And so what you want to do is look at the angle that we know. We know angle C. And so what I should do is try to solve for side C. I want to use the version of the law of cosines that has C squared, because C is the angle that I know. So C squared is equal to A squared plus B squared minus 2AB times the cosine of C. And so again, cosine of C, I know C, that's why I'm using this form of the law of cosines. And so I'm going to plug in all of the information that I know. I don't know side C, that's actually what I'm trying to solve for. I do know A is 112, and that's squared. I know B, which is 135, and that's squared, minus 2 times A is 112, times B is 135, times the cosine of angle C, which is 104.3 degrees. Okay, so I'm going to want to work this out, and I'm going to want to try to take it one step at a time. You can type all of this into your calculator at once if you're proficient with your calculator. Otherwise, you might want to take it one step at a time. So what I'm going to do is start here with C squared equals. I'm going to square 112, so 112 squared. I'm going to get a big number, 12,544, plus 135 squared. 135 squared is 18,225. Minus, now I can go ahead and multiply all of these together. Okay, so I can do all of this at once. I'm going to do 2 times 112 times 135 times the cosine of 104.3. And I get a negative number, so I want to make sure that I'm careful here. I'm subtracting a negative number. So I'm subtracting negative 7,469, and I'll go ahead and go out to a couple decimal places here, 25. Okay, 7,469.25, negative. So I'm subtracting the negative. And so c squared will be equal to, so I'm going to add these together and subtract this negative, which is adding, right? Subtracting the negative is adding. So I'm going to add all of these together. I've got 12,544 plus 18,225 plus, because I'm subtracting the negative, 7,469.25. When I add all of these together, I get 38,238.25. Last step is to take the square root of both sides. So the square root of c squared is c. Right? The square root cancels the square, so I get c equals. And I need to take the square root of this number, so the square root of 38,238.25. I get 195.55. Okay, the book probably rounds this to 196 meters. Okay, so now we know the length of side C. Now I know C is 196 meters. Now that I know an angle and the side opposite that angle, now I can use the law of sines to finish solving the rest of the triangle. And so the law of sines says that A over sine A is equal to B over sine B is equal to C over sine C. And so C is the information that I know, the side and the angle, so I definitely want to use that. And it doesn't really matter if I use A over sine A equals C over sine C, or if I use B over sine B is equal to C over sine C. It makes no difference. I'm going to get the same answers either way. And so I'll use A. Let's use A over sine A is equal to C over sine C. So I'll plug in the numbers I know. A is 112. The angle A is what I'm looking for. Side C is 196 meters, divided by the sine of C, which is 104.3 degrees. And so I want to get sine A out of the denominator. I multiply both sides by sine A. I'm going to multiply both sides by sine of 104.3 and divide both sides by 196, so that I'll end up with sine A equals 112 times the sine of 104.3 degrees divided by 196 meters. Really what I'm doing here is cross multiplying. So 112 times sine, right, 112 times sine. On the other side I would get 196 sine A, but then I need to divide by 196. So I'm cross multiplying and dividing. That's how I'm solving these equations that way. Okay, so I'm going to work this out first. Sine A equals, and so we have 112 times the sine of 104.3, close parentheses, divided by 196, and we get 0.5537. Now I can take the inverse sine of both sides. So the inverse sine of 0.5537 is 33.62. 33.62 degrees. And so now I know angle A. Angle A is 33.62 degrees. And the only thing left to find is angle B. Of course, I could use the law of sines again to find angle B. I could even use the law of cosines to find angle B. The easiest way, though, of course, is that they are all three supposed to add up to 180. So angle B should be 180 minus angle A minus angle C, which is 180 minus 33.62 minus 104.3. And so we'll type this in. We have 180 minus 33.62 minus 104.3. And, oops, I made a mistake. Let's try that again. 180 minus 33.62 minus 104.3. And we get 42.08 degrees. 42.08 degrees. So angle B is 42.08 degrees. Notice here that I don't have to worry about whether there's one solution or two solutions or three solutions. Because I knew two sides originally and the angle in between them, there's guaranteed only to be one solution. If I have an angle of 104.3 degrees and I know the lengths of both of these sides, there's only one way to put in the third side. There's no other option. So there's always only going to be one solution when I apply the law of cosines this way. This is example 2. It says if A is 375 feet, B is 282 feet, and C is 114 feet, solve the triangle. And so again, sketching out the triangle will help us visualize the problem. We have angles A, B, and C, and sides A, B, and C. And we know the length of all three sides. A is 375.0 feet. B is 282.0 feet. And C is 114. Now, obviously my triangle is not drawn to scale. That's not the point. It just helps me to lay out the information. And so I know all three sides in this example. I don't know any of the angles. And so the law of sines is not going to be helpful to me here. But I can use the law of cosines to solve for one of these angles. And since I know all three sides, it doesn't matter which angle I solve for. And so I will choose a squared equals b squared plus c squared minus 2bc times the cosine of a. Okay, and we're trying to solve for a. That's the angle that we don't know. We know all of the sides, right? A, B, and C, B, and C. We know all of that information. We're trying to solve for angle A. And so, two ways to do this, really. I could go ahead and plug in all of the numbers, work out what I know, and then solve for A. I could rearrange the equation now and solve for A first, and then plug in the numbers, and then punch that into my calculator. Whichever way works for you is fine. Maybe it's easiest if we plug the numbers in now, calculate what we can, and then solve for A at the end. And so that's what I think I'll do. A is 375 squared. B is 282, that's squared, plus C, which is 114, squared, minus 2 times B, which is 282, times C, which is 114, times the cosine of A. So I'm going to work out as much of this as I can. I'm going to go ahead and square these. I can go ahead and multiply 2 times 282 times 114 as well. And so that's what I'll do. So we have 375 squared, which is 140,625. That equals 282 squared, which is 79,524. Plus c squared, which is 114 squared, 12,996, minus, and I'll go ahead and multiply these out, 2 times 282 times 114, 2 times 282 times 114, and I get 64,296, okay, times the cosine of A. This time when I multiplied, the answer came out to be positive. There was no worry about having to subtract a negative here. And so what I want to do now is, my goal is to get the A by itself, right? I want to solve for A. I can go ahead and combine these like terms. This is not a like term though, it has a cosine A in it. And so I can only add these two together. I'll go ahead and do that first. I'll leave this as 140,625 equals, let's add 79,524. Plus 12,996, and we get 92,520, and then I'm still subtracting here, 64,296 times the cosine of A. And so my goal is to get the A by itself. Let's subtract 92,520 from both sides. Okay, they'll cancel over here. we're left with negative 64,296 times the cosine of A. And over here, when I subtract, we have 140,625 minus 92,520, and we get 48,105. Okay. Now I need to divide by the coefficient of cosine A here, so I'm going to divide by negative 64,296 on both sides. Cancel over here. We're left with cosine A equals, and so we've got 48,105 divided by negative 64,292, and we get negative 0.74823. And so the more decimal points I carry until the final answer, the better, in my opinion. And so now to solve for A, I need to take the inverse cosine of both sides. So A will be the inverse cosine of negative 0.74823. Okay, so the inverse cosine of negative 0.74823. And we get A is equal to 138.4 degrees. So now we know angle A. Angle A, we think, is 138.4 degrees. Okay, 138.4 degrees. And again, my triangle is not drawn to scale. Obviously 138 is greater than 90. The triangle is supposed to be obtuse, so I didn't draw it that way, but that's okay. This is just to help me visualize. Now that I know one of the angles, and I know the side opposite that angle, now I can use the law of sines. And so I will use A over sine A is equal to, it doesn't matter if I use B or C, I'll use B over sine B. Okay, and so here the angle B is what I'm looking for. I know the sides A and B, and I know angle A, so I'll plug in that information. A is 375 divided by the sine of A, which is 138.4, and that equals B, which is 282, divided by the sine of B. Again, I want to cross multiply and divide these to solve for B. So, well, for sine B at least for now. Sine B will equal 282 times the sine of 138.4 divided by 375. And so the sine of B will equal, we have 282 times the sine of 138.4, close parentheses, divided by 375, and we get 0.49927. 0.49927. Okay, and so now we can find B by taking the inverse sine of both sides. B is the inverse sine of 0.49927, and so B will equal the inverse sine of 0.49927, close parentheses. We get 29.95 degrees. 29.95 degrees. So angle B is 29.95 degrees. Now that I know two of the angles, the third one is easy to find because they have to add up to 180. So we take 180 and we take away 138.4 and we take away 29.95 and we get 11.65. 11.65. And so again, clearly my triangle is not drawn to scale. It would probably really look something more like this, right? Where this angle is the 138.4, that's angle A. Angle B is 29.95, that's angle B. And angle C up here is the 11.65. And then the sides that I have are 375, this was given to me. Side B is 282, and side C is 114. Okay, and one way to know whether or not you're getting the right answers or not is to compare the angles to the sides. The smallest angle should be opposite the smallest side. So angle C is opposite side C. That is the smallest angle, and that's also the smallest side. The biggest angle should be opposite the biggest side. So that's just one way to check to see if you're at least on the right track.